Hey everyone, welcome back to University of Montana GEO 572 Advanced Hydrogeology. So today we're going to continue our talk of dispersion and try and work towards deriving the advection dispersion equation. So let's go back and remember what we had talked about with dispersion.
Okay, so we're going to continue where we left off, talking about dispersion, and recall that we said that we'll never know the total fluid velocity distribution in a groundwater field. There's just too many variations between the pore throat network and the geologic heterogeneity. And so we said that we could describe the flow at a point as being equal to the average velocity plus some random velocity that comes from a random distribution. All right. So this guy, this is our fluid velocity at the point ijk, and it's a vector. Vector at I, J, K, and VI, JK is the average fluid velocity, and V hat is the random velocity fluctuation. All right, and we said that this random velocity distribution leads to a process called mechanical dispersion. And mechanical dispersion was this mixing due to random velocity that we don't know. This V hat. All right, and there are some properties that we should think about with mechanical dispersion and this velocity distribution. And the first is that V hat, the distribution V hat is not the same in all directions. Sorry. And the distribution is governed by the pore network. It's governed by fluid flow velocity variations that are sort of driven by groundwater processes. So it's not the same in all directions. So for example, but we're going to say that V hat is normally distributed. Is assumed, this is an important assumption, to be normally distributed. And so what I mean by these two things is that we might have for each direction. So let's consider a velocity variance here. So this is it's called a probability distribution function, a PDF, and it's the normal. So this is the probability of some velocity. So let's say this is v hat x, the probability of some velocity variance. And the most likely is that the v hat is 0, all right? And then it follows a bell-shaped curve so that as v hat x gets bigger and bigger and bigger, it becomes less and less likely. So the probability gets less and less likely. And this probability can be described, if it's a normal distribution, by the standard deviation, sigma sub x. That gives us the parameter that describes the shape of this bell-shaped curve, right? And this is the standard deviation. Sigma x is the standard deviation of our random velocity distribution in the x direction, v sub x, all right? So we might have one distribution for v sub x, and let's say that let's put some numbers, just arbitrary numbers here, and let's say that this is 10 and this is minus 10. And I'm just putting these numbers here as a reference, because if we then looked at, say, the distribution of velocity in the y direction, this distribution is probably not the same. And in fact, oftentimes it's a little less variable. Well, let's just say that in this case, it's less variable, so that, let me put my relative numbers here, 10. You see that our standard deviation is tighter. And the probability of having this random fluctuation be, say, 10, positive 10, versus negative 10 is much lower for y, right? And similarly in z, we might have just another distribution. All right, and sorry, this is p v y. This is the probability of velocity, of the random velocity in the z direction. And again, so this is vz, and our most probable value is here at 0, and this one might drop off really fast, right? As an example. And so here's minus 10, and here's 10. And these now are characterized by sigma z, which is the standard deviation of the velocity in the z direction, all right? So we assume that the velocity distribution follows this kind of probability distribution. Most likely value is 0, and then it falls off according to a normal distribution on either side. All right, and that these normal distributions aren't the same in all directions. All right, so here we have different bell-shaped curves or different velocity distributions in the x, y, and z direction. Okay, so these velocity distributions lead to spreading of solutes. So let's think about, as an example, let's look in map view at a point source of solute. So we start off with this point source. Let's remind ourselves this is map view. And And in this view, the coordinates system looks like this. Here's the x direction. Here's the y direction. All right, and we start off with a point source. So at time 0, we put a drop of some solute in our groundwater flow direction, and the mean groundwater flow is here. All right, this is our average groundwater flow. And at some time later, down the flow path, our solute pack, we drop it in right here, and then it moves along with the flow velocity. And dispersion is going to spread this thing out. So here's a couple contours of our solute now, and you can see that it's spread, all right? And it gets spread out laterally and in a transverse direction. But that these spreading lengths, bound and this, they're not the same, all right? And that's because there's no reason that our velocity distributions have to be the same. So for example, this lateral spreading is due to the distribution of v hat x. And the transverse here in the y direction is due to v hat y, right? And these distributions aren't the same, so we don't get the same spreading. All right. So if we were to look at the concentration profiles here, so if I were to draw here the concentration, and let's say this is 0 and this is C sub naught, which is the concentration at T0. So here's C sub naught. So this is at time T0. My constant, and this is the x direction. My concentration profile would look like this. Come up to C naught, right over our point, and then it'd come right back down. Right, so this is at T0 at our initial place. If I drew this same breakthrough, or this is not a breakthrough curve, if I drew this same profile curve, all right, we would see at some other time, all right, we would see, and here's again my x, and here is C naught, all right? So now I'm drawing this one a little farther down in x. We would see that our concentration profile would look like this. And I'm sorry, it would not go to C naught. So I'm going to redraw this. We would find now that our concentration profile at this new time, keep doing it. So I'm gonna have to keep erasing it until I might look like something like this, all right? And it has, again, a bell-shaped curve. And here's the location of the average. And this bell-shaped curve is characterized by sigma L, where sigma L is the standard deviation of concentration in the lateral direction. And in this case, that's x direction. All right, that's, or longitudinal. This is not lateral. I'm really, I apologize. This is longitudinal. It just means in the direction of the main flow. All right. So this down here we need to change, not in the lateral, in the longitudinal direction. All right, so it makes sense. If my velocity distribution is normally distributed, then the shape of my concentration curve will be normally distributed. And sigma L is the standard deviation of the concentration in the x direction, all right, of my, my point after it's been transported. Now the distance of the center of the plume, so this x bar, well, x bar, the center of the plume, or center of, it's not really a plume, what would we call this? Center of our mass point, or our solute, is given by the average velocity, so v bar x, times the time, some time that it took to get here. All right. All right, so the center of the plume will be at sort of the distance given by the average velocity, but this spreading, sigma L, will result from sigma L is due to our random velocities in v sub x. All right, and so similarly, we might have a distribution in y. We might draw our concentration profile in y. All right, and we would see a different amount of spreading. So, for example, in y, so here's C naught, here's y, and at time equals 0, our pulse, our little dot of concentration in y looks just the same. But if we were to come now to this next position and draw a y profile, we would see that transverse direction, that our concentration profile would be sharper. It wouldn't be as spread out. All right. And here, this would be, actually wouldn't have moved any. It's just y naught, whatever this is. And this is our transverse. So this is sigma t. Sigma t is the standard deviation in the transverse direction. Okay, so we can do this, we can think about this also in cross section. So if I were to draw in cross section my plume, so here's the top of an aquifer, let's say. Put a tree there, happy little tree. And here's the bottom of the aquifer, an aquitard. And again, our flow is in this direction. So here's V bar. But now our coordinate system is X and Z. All right, and we put our little plume of solute in here. And then this is at T naught. All right, and if we were to go sometime later, we would find that it is spread out vertically as well. All right, so again, this is the longitudinal spread. And this now is the transverse horizontal, or sorry, transverse vertical spread. All right, so, okay, if we drew the x direction, we'd get exactly the same curve we drew up here. But now let's draw our concentration profiles. Here, this will be in the z direction, all right? And here's C naught. And at time t equals 0, our concentration profile looks just like it looked in all the other directions. And then if we move down to this next time and we were to draw a concentration profile in the z direction, it's going to be given by this very short spreading path. And so we might see something like z, here's C naught. We would see something like this. All right, and here we'd have sigma z, the standard deviation for the concentration profile in the z direction. Okay, so these, the spreading, so our spreading of solute here, right? As we move from our point source, it flows along with the velocity field and it gets spread by our random velocity distribution. So it's due to our random velocity, right? And if we assume v hat is normal, then we can describe, then it turns out that, that the spreading is driven by the gradient in concentration So as an example, the C dx would be the gradient in concentration in the x direction, all right? And we call this a Fickian process. Which means that we might say we want to describe the flux due to dispersion. Mechanical dispersion. Actually, let's call that a J because that's what I've been using for solute fluxes. J dm, we might say is equal to So this is what a Fickian process means. All right. Now, if V is normal also, so here's sort of the first implication of V being normal. The second implication is that the variance in, or the spreading, is due to this dispersion transport, all right, this dispersive transport. And so we can characterize the dispersivity. So the mechanical dispersivity, for example, in the longitudinal direction is equal to sigma L squared over 2 times time. And all this says is that the dispersion coefficient here is basically equal to the variance, or the standard deviation, or how far the spreading is. So the more spreading you get, the wider your plume is after, or your point source is after being transported, the higher the dispersion coefficient. All right. And so this happens for all of them. The mechanical dispersion coefficient, so dm transverse horizontal is equal to alpha th squared over 2t. So in the case we're talking about here, this would be the x direction, y direction, and this is for flow in the x direction. So this lateral or longitudinal just means in the direction of flow. For our situation here, it's in the x direction. dm tv, so mechanical dispersion transverse vertical would be the variance in the transverse vertical direction over 2t. All right. Okay, so we can collapse dml, dmth, dmtv into a, so we take all of these guys here and we collapse them into a big thing, dm bar, and this guy is called the dispersion tensor. Let's call it the mechanical dispersion tensor. And it's a tensor because it has directional dependence. It depends on the way the water's flowing, and it also depends on how that lines up with the geology. So this depends on the direction of flow. And the orientation of geologic structure. And in general, this dispersion tensor is really complicated because we could have flow going in all different directions, and they may or may not be lined up with geology. Geology could have very different dispersive properties, so the pore throat networks can be aligned very differently. And so in general, this dispersion tensor's got a lot of stuff, and it, you know, it's really complicated. And all I want to say is that, like, in general, it has 81 terms. And that's because you could have this thing oriented in all different directions. And so one of the simplifications that we make is remember that the world's made up of these long, flat aquifers. And so we're going to say that in general, the the flow aligns with the principal direction of dispersivity. So in general, we're going to have a single value of dispersivity in the direction of flow, and then we'll have transverse dispersivities that are different in the horizontal and vertical directions. So in general, we're going to reduce this. We almost always assume that the flow and major dispersivity axes align. And so we're going to have essentially three terms: dl, d alpha, or dth, and dtv. I'm going to put the m there for mechanical. We're almost always just going to reduce it to these three terms. Okay, so all I really want you to, I want you to understand that the dispersivity tensor is really complicated, and I don't want to get into the details of that because that's a lecture in itself or three. But it depends on the direction of the flow and the orientation of the geologic structure, and that I have struction here. That doesn't make any sense, so I'm going to change that. That if we say that the direction of flow is oriented along the main geologic structures, and so along the main axes of the dispersion tensor, that we can simplify it to three terms. Okay. So we're gonna do something else here, and we're gonna talk about this dispersion. So let's consider, for example, the mechanical dispersion coefficient in the longitudinal direction. All right, and we're going to make an assumption here. We're going to say that, well, let's say that my distribution of the variance in velocity is proportional to the mean velocity. And that makes sense. Like, the faster you're going, then the more spread you might expect. The faster the mean velocity is, you know that the lowest velocity is going to be 0. And so you're going to have a higher standard deviation in velocity. So we're going to say it's proportional to the average velocity in the longitudinal direction. And anytime we do that, we can always write it as a fudge factor. So alpha longitudinal times v star L. And so this is, remember, DML is my dispersion coefficient. This is the mechanical dispersion coefficient in the longitudinal direction. So along the direction of main flow. All right. V bar sub L is the average velocity. In the longitudinal direction. All right. Should basically just be equal to the average velocity in this case. And alpha L is the dispersivity. All right, and this term, dispersivity, the dispersivity here is is this alpha L guy. Let's talk units. So the flux J dispersion, right? We said that's going to be equal to the moles per time, so per second, let's say, per meter squared. All right, that's my flux. All right. So we said that J dispersion would be equal to dml. Let's put this in the longitudinal direction. Negative dml times dc dx, for example. All right. So dc dx, that's moles per meter. So remember this, we know this is moles per second per meter squared. This guy here is moles per meter cubed per meter. All right, so this is going to end up being moles to the moles times meter to the fourth. All right, so how do we make these two equal? Well, our dispersivity has to be equal to meters squared per second. If I do that, meters to the fourth and meters squared will cancel, and I'll have meters second. All right, and I'll have moles per second. So dispersivity has the units of meters squared per second. All right, so now let's look at if this guy is equal to alpha L times V sub x. We know we have meters squared per second, and velocity would be meters per second. So dispersivity has to have the unit meters. All right, so dispersivity has the unit length, or meters in this case. Okay, so for flow, we're going to have longitudinal dispersivity. If we assume that our dispersion tensor aligns with our direction of flow, which aligns with the geologic structure, we have three coefficients. So we've got dml, which is equal to our alpha L times V. All right, and alpha L is the longitudinal dispersivity. All right, dm transverse horizontal is alpha th times V. Alpha th is the horizontal transverse dispersivity. All right, and dm tv is equal to alpha tv times v bar. Alpha tv is the vertical transverse dispersivity. Okay, so mechanical dispersion is due to the random velocity variations. If we assume a normal distribution, it's Fickian. So now we're going to talk about combining diffusion and dispersion. All right, they're both Fickian. They're both driven by concentration gradients. And so we can think about how we might combine those two. So let's do that. So let's say that because both diffusion and dispersion are Fickian. And remember, this is based on the assumption that our velocity distribution is normal. They're both driven by concentration gradient. So for example, consider 1D in the x direction, longitudinal only, dispersion and diffusion. Now let's just take an aside here. Diffusion is due to random velocity fluctuations of atoms, and it's only dependent upon temperature, and it is independent of direction. All right, so molecular diffusion is not directional dependent. It is not a tensor. And so the only thing that adds directional dependence is dispersion, where we have differences in the velocity distribution with different directions. All right, so diffusion is not a tensor. Okay, so in this case, my diffusive flux, so J diff, right, my diffusive flux is equal to negative D star dc dx, where D star is my aqueous D star is my aqueous diffusion coefficient. All right. All right. My dispersion flux is equal to negative dm L dc dx. All right. And I can combine these two. So we combine diffusion and dispersion by saying J dH, and I'm going to is equal to J diff plus J disp. All right. So this is equal to negative minus DML plus D star times DC dx. All right, I've just put these two guys in here and did a bit of algebra. All right. And I'm going to take it one more step. Negative alpha L V x plus D star times dC dx. And this is from our definition of dispersivity. All right, so let's do some vocab now. JDH, we're going to call the hydro. Well, let's not define this guy. This guy's just a little different. Let's combine these two into one big term, D sub H. All right. And D sub H is the hydrodynamic dispersivity, dispersion coefficient. All right, and the hydrodynamic dispersion coefficient includes both diffusion and dispersion. All right, and it is equal to alpha V bar, and this is alpha sub I V bar plus D star. All right, where this is the molecular diffusion coefficient, this is our average fluid velocity, and this is the dispersivity in the I direction, right? So DHI. So DH, because it has this dispersivity, which is directionally dependent, it's a tensor. So DHI is a tensor. And it has the same terms as the dispersivity, the mechanical dispersivity or dispersion, but it just includes both dispersion and diffusion. Okay, so the hydrodynamic dispersion coefficient includes both incorporates dispersion and diffusion. Let's think about some properties of it. So in general, alpha V star is much bigger than D star as long as V, for most systems in where groundwater velocity is much greater than 0. All right. And this is, we'll talk more detail like when we expect V bar to be great enough to be greater than diffusion. But for most cases, this dispersive term is greater than diffusion. But when the fluid velocity goes to 0, then our DH goes to D star. All right. So when fluid velocity is really low, then our Fickian transport is dominated by diffusion. Okay. So that is the hydrodynamic dispersion. It includes both diffusion and dispersivity. The dispersion coefficient is a tensor. It's directionally dependent. We're generally going to define it in the longitudinal direction, transverse horizontal, and transverse vertical. All right. I want you to know that we made some big assumptions to do that. All right. We assumed that the dispersivity tensor is aligned perfectly with the fluid velocity vector, and that our dispersivity doesn't change when the fluid velocity vector changes. In reality, that's not the case, but it's an assumption we generally make. So we can combine both of those into one Fickian term, all right? And that's going to help us for our next lecture when we derive the advection dispersion equation. We can lump both diffusive and dispersive fluxes into the hydrodynamic dispersion. Okay, I'll end the lecture there, and I'll see you guys in class.